Welcome everyone to our practical lecture 0.1 in our cloud computing and big data course today. The idea of the lecture is really, before we even start with the course, to get a little bit of brush up of Python and Jupyter and to understand a little bit about remote execution via a browser versus a local execution in a browser based on localhost. But before we dive into the material into the practical lecture 0.1, let us review what we had the last time. In the prologue, we discussed a little bit the course motivation and of course then also the course organization, how we basically go with assignments and so forth. In the course motivation, we had the idea that you see a little bit about here in this graph. So essentially saying that we have this interesting two areas where we say big data is not only a hype anymore, it is really there, it exists, it's a problem in many regards, not only in volume, as we said, also here and there, maybe in velocity, when we said that we have lots of tape archives, which are multi-petabytes, no problem at all to keep big data, but to access them very quickly is very hard. So basically, it's a very long time to tape, getting it from tape out to disks. So when you now think that some of the square kilometer array, for instance, a scientific example, will generate 1 petabyte per 20 seconds, our tape archives will be growing very quickly full. And the same is true, of course, for basically big cloud providers like Facebook that accumulate data more and more, making it basically very harder to analyze this data, to process this data in real time. If you think about Facebook, of course, is a good example. When you want to click something which you like, then you also want to see this like and not only a like in 1 hour. So for this, there are lots of interesting techniques that we will also look into this course more and more. And what we said in terms of big data, one of the interesting things to make use of it is by far today deep learning, which is a very special branch of machine learning based on neural networks. And basically, it depends really if you are having big data, then you can go to these deep learning networks. But if you are not swimming in data, if you have, let's say, small data still, then the traditional classifiers, the traditional learning models still have very much the relevance. And basically here and there even better than deep learning models, because deep learning really needs usually big data to work well. Now, when you do this, the accuracy you see here on the left-hand side is then that you get certain accuracy. And if you have big data, chances are that you basically really need to go to new frameworks, to new technologies, because if you go to the normal laptop way of using a little bit R on your laptop, scikit-learn, Veka, MATLAB, Octave, all of these more serial implementations of algorithms, chances are that your laptop not going to make it with big data. Your memory will be basically crashing very quickly. Now, if you want to do then neural networks at scale and starting with really, let's say, moderate deep learning networks or large deep learning networks, which have a very high accuracy also in our research in the last couple of years, of course, there's one side remark which brings this course into the focus. And that means the more you go to the big, large deep learning networks with cutting edge performance and hyperparameter tuning automatically, you have to pay the price. And the price is usually the training time. And this means lots of computing. So this is basically infeasible on a laptop anymore, right? You have to go to the cloud, you have to go to high performance computing systems in order to work well. Admittedly, this means only for big data. When you have small data, as I've said, doing your random forest on a small laptop can still beat neural network in the sense if you don't really swim in data. However, I also showed you last time as a motivation that we are living in a very interesting time, and it's really glorious if I remember you that, when I basically 10 years ago had some students, we implemented lots of different frameworks ourselves, neural networks with MPI in parallel. There were just simply no packages. Nowadays, you download all of these packages for free. TensorFlow, PyTorch, Keras, all open source packages, which are very scalable, combined maybe with Horowat, for example. But then you have really stable software that works well. On top, we have a glorious time that the hardware accelerators with GPUs like A100s these days are really cutting edge tensor units that can process neural networks at an incredible speed. just thinking about that 5 years ago, 10 years ago is also an interesting momentum that many of you are not aware, but those of you that maybe know a little bit about computer architecture, where we were stuck with CPUs and the problem of getting too much heat on the chip, now the GPUs have really done there a lot. And then, of course, needless to say, big data is coming more and more. If you follow Gabriel's course, which is one of the, let's say, complementary courses here, you see big data, satellite data with ever more performances, ever more accuracy and granularity. The Sentinels have much more resolutions, more bands. They basically come with lots of more big data, really, that we have to interpret. Also, the cost of storage is not extremely high anymore. As I said, that depends a little bit. So if you go into the high petabytes, of course, then still you have the tapes, which are not so expensive, perhaps, but then also not accessible. So it depends a little bit how often you want to access it. But in generally, the situation with data has been never better. Even journals press scientists to open up the data, right? If you want to publish something. So there's a good and interesting time now that having these key ingredients, big data, the right hardware that we have in clouds and high performance computers, and also the software is basically for free all over the place. This is an interesting time to create, for instance, new products for startups. I was alluding to apps which are now coming up basically every now and then on Facebook, right? So identify this flower automatically, identify this rock formation automatically, how old is a tree? These are all very simple apps based and fueled by these basically 3 pillars that you see here down in the slides. Now, the interesting thing is you can also do that with something where I explained to you soccerwatch.tv, where one of my PhD students basically aborted his PhD, but then really helped that company with his knowledge really in neuroscience analysis to really make a difference in, you know, watching football automatically, basically creating an AI cameraman. And with this, a new branch was basically established and they got lots of investor grants. And this was also only possible because the access was there. So there was these kind of 3 pillars again available to this small startup. And now they actually expand to basketball, to volleyball, and watch sport online. So take a look at this. It's quite an interesting, impressive example. Now, of course, organization-wise, I think it's, of course, clear we do most of the things basically in our Canvas environment, which more or less has been now, you know, completely activated. In the past, we had still some things on UGLA, and we still have some things on UGLA, but I think it's mostly for the professors and not for you students anymore. So you basically can follow the course completely, essentially in our Canvas environment. And then we basically will have, of course, access here and there to all the different cloud systems. Just yesterday at the workshop, I talked to 2 or 3 fellows. Do we really will use real cloud vendors? And the answer is yes. At least we want to try to the best possible degree. And speaking of that, would be probably Amazon, Google Cloud, and Microsoft Azure. Also here and there, we will use the Jupyter environment of the Jülich Supercomputing Center. But of course, the idea of the course is also to explore really real clouds in the assignments, and then also get a bit in touch with Apache Spark installation, Hadoop, and most notably, that brings us also to Python. So Python in data science is the modus operandi today. While R was there in the past, I think the majority, except maybe some fields like bioinformatics or so, they still rely a little bit on R maybe, but many of the different scientific domains switch heavily to Python. And this reason is because there are beautiful packages in Python. And hence, this is one of the reasons why before we even start the course here, we will do a short brush up of Python and also about the Jupyter environment. We do it very shortly here because many of you had probably the course from Ingolfur, or when I said raise hand, if you know Python, I think almost everybody of you already has raised the hand, so you know Python in generally. So I put my emphasis a little bit on those things where, you know, there are lessons learned, where often traps for students exist when they do the assignments. This is one of the ideas so that the assignments go smoother before you start them. So this is one of the additional lectures that is more kind of a helper lecture. If you're a professional in Python, if you know Jupyter notebooks in and out, feel free to, you know, skip this course. But here and there may be some still lessons learned that capture the essence where lots of people do some certain errors, which I see again and again in the answer of assignments or in, let's say, office hours or question and answer sessions. So we start here a little bit with Python environments, and here again, it's more pointers for you to understand that NumPy and Pandas today is something when you really want to go to data science, you have to know them. We go then a little bit in the preparation of deep learning. This will come up in lecture 6 and 7 later, but we will also look a little bit why Python has relevance in those packages. And this is the same for PyTorch, basically another deep learning package. We will try to understand a little bit now distributed setups of Jupyter versus a local setup with Anaconda, for instance. This is a very different beast, but sometimes people that not previously have worked so much with cloud computing here and there have to still understand a little bit. And we'll have some, really practical insights, which also marks the idea of this practical lectures. Whenever you see that practical lecture, indicates here in the course that I will demonstrate something. And of course, you are welcome to redo what I'm doing, but mostly this is also covered by assignments, right? So needless to say that I will do practical lectures often when there are assignments around, let's say deep learning, or also when we have the, let's say, regression topics for the clouds, which will come up very soon, and so on. So I will demonstrate a little bit this remote versus local setup. So then the second part will be more that we look into some basic structures of Python. Again, for those that are really Python experts, there's no big news here, except maybe here and there that we will look on some problems between lessons learned here and there, as I said, from some assignments where people always overlook sometimes things like a vector in Python, for instance, or so on, could be looking differently if their dimensions not really are well specified, and those don't really work as a vector anymore, but are rather just a collection of numbers, for example. Towards the end, then we will look basically in the Helmholtz Data Federation Cloud in a real use case. We will start to look at here. It's something called the MNIST dataset to analyze handwritten characters. We do there just a data pre-processing application. And then I show you a little bit how you can maybe go out of, shopping data, take that shopping data to a cloud, and then basically do some nice association rule mining just with Python and the simple of packages, which is one of the powerful statements I want to do also with this last part here. Just by introducing ML_extend, you can just basically quickly, go to some shop and say, hey, I can actually give you some insights on your shopping data if you have a, let's say, proper shopping list for me. So it's a very easy way of basically directly start in context with data mining. So let's start with the, this is maybe a good disclaimer, just that of course, this is not really a Python course, right? So for those of you that never touched Python and want to do data science, I think it's good that you look more deeper into Python, looking more into a real proper course on it if you want. This is really just putting here and there some emphasis on things which are relevant for the assignments, and also where I know there's some lessons learned to be taken. Okay, so going back to the machine learning prerequisites, just where we now going to locate ourselves here today in the course, we said machine learning is basically derived by the idea that some pattern exists. So you have some data and you think there is some pattern that we want to analyze, like the shopping behavior we just mentioned, right? But you also can imagine that there's no precise mathematical formula how people shop, at least not in this particular shop, or basically not in this particular, let's say, field or type of shop. And if you have these ingredients, then you also need, of course, data. Now, handling this data to do learning from big data seems easier than done. So basically, if you have real life data, it's really messy. It never comes really in a very proper format. Instead, I mean, basically, you have that maybe if you have a, let's say, demo tutorial or things that you get from me here in this course or in the machine learning course. But if you go to really practice, and get the data from firsthand from a shop, it's really usually ugly, missing values, noisy data. Hence, Python is there to also look at pre-processing, cleaning the data, creating data structures with Pandas on top maybe. So you have to find the way from getting the pure data you get basically for machine learning or data mining. It doesn't mean a big difference. If you remember, data mining, applied statistics, machine learning, they all have an overlap in data science fueled by computing. But in the end, Python is there not only to process the data, so to speak, directly to do data mining, but also it plays a huge role in preparing data. Use one-hot encoded for several algorithms, a very special technique, for instance, required by some algorithms. So Python is a very powerful tool in many ways. And we will hear in lecture 11, actually, from one of my PhD students, Shadi, who does lots of these investigations from shopping data, for instance, firsthand from real shops, how ugly it is and how helpful Python can be if you basically use that for structure data and getting into a, let's say, way that really algorithms in machine learning and data mining can use it. So from the Python programming language perspective, I think many of you know it already. It's a script language, so much more easier to program than compiling, for instance, in C with C and then have an executable and so on. That are things that we do in the HPC course because it's still relatively fast. In HPC, we are very interested in very fast performance. In fact, in the HPC course and in HPC in general, people still use Fortran, right? Because it's also very incredible fast and has been standing the test of time. And however, if you look into data sciences perspective, cloud computing, using it with data sciences, machine learning, deep learning, Python is definitely the modus operandi. And it's also here and there, not massively here and there slower because we have good packages and then also good, let's say, hardware that maps these problems like multi-matrix multiplication and so on, which is really one of the ideas. So you see here a very simple start script, which is, I think, very quickly to understand. You have a very nice support for strings. If you think about in the C world, you would have a characters of, chars that you basically put together in an array for a string. So here you have a very nice support for strings. The way how you can combine really mathematics, as you see here, with then basically real computation. And a string again is also nice shown here. So basically, it's a perfect language to be very fast, right? And you can really create applications very rapidly. And of course, for this machine learning modeling, which means many changes again in terms of parameters, maybe you change the architecture of a model, maybe even the algorithm. If you're not happy with random forest, you maybe quickly shift to support vector machines. So things go quickly in this field. And with this, it's basically with Python, a very nice language before you compile again, and execute again, etc. Another idea where I said Python is really a very, very nice language is all the library support. The import statements we come to later, the math library, NumPy, lots of different good libraries are there. MLXtend, as I said, for association rule mining and shopping data. So, and this goes on and goes on. There are so many Python libraries that it is really nice to work in Python. Chances are that someone has already something implemented in an algorithm and you find it online. And we take advantage of this in the course. And the way how you program it is, of course, a little bit different when you come to machine learning in this regard, that when you basically have a proper C program or whatever, big bang program you want to program, you have basically a more classical programming thing where you would say there are certain rules how you operate a bank, you have certain data that the bank needs, and you have some application logic for classical programming, and then you get the answers. Right, so this is something what was more the classical programming here, and the rules were very strict, not learned, but given. Let's say people which have, let's say 100 million on the bank account, they get a good credit, something like this. Here in machine learning, the things are different. So basically, you have lots of answers from previous customers already there, right? That's where you learn from. And then basically the data gives you in the data that you have for one customer and so on. Then you'd learn from these basically certain new rules and see from experience or basically from the data itself, these are these and these rules. I could go on and go on with this, but just to realize that, of course, when we think about machine learning and deep learning and so on, the way how you program is a little bit different. Also, what you learn probably in software development with Matthias Bog. So machine learning is a different way how we model things. I will come to this again when we talk also about the CRISP DM process later on. A good book in this regard, if you really want to learn more in this, is this book. I found it's open, usually accessible, if you want to really start with deep learning in this part. Just to introduce NumPy a little bit, you see here a very beautiful code snippet where you don't really have to do much. You have to import NumPy as a basically here a statement as NP is usually a convention you use. It's not has to be not this way, but NP is most in use, and then you have a random number here that you can pull in, and you can basically create a vector here. The vector is recognized by these two brackets here, and with just 3 lines, right? So this is quite nice, and basically often used in many of the programs we do. And of course, you see here, just without doing too much introduction on that, I'm sure many of you have already used it. It's basically used in lots of different software. It is very efficient when we use it in machine learning for, let's say, generic data containers, when you do vectors, matrices. It's really one of the most important libraries that you can find in data science. So knowing that is definitively a good idea. And the same is actually true today also for the Pandas Python library. There, for instance, data frames, which are often used if you want to read a data set. One I will demonstrate in the second part of this lecture here, really practically. You see here a comma separated values file, right, which is a certain structure in files, how you do, for instance, shopping data and so on. You can easily do a read here with a couple of lines. You have actually, with Pandas, then have a data frame created, which you can really nicely handle inside the Python environment, out of this real world, let's say, data set. Here's another example how you can quickly create your own data frame based out of a NumPy array we just have seen. So essentially, again, a matrix, so to speak, here with some columns, very quickly created. So also here, a very nice tool working together with NumPy very nicely, and is also often used in practice. Then, as I was asking you if you know much about deep learning, so there are some people raising hands, but not all of them. So I think here we have some people that maybe don't use TensorFlow before. This is a Python library again, or really a tool set, a framework really, based on essentially tensors, and I will explain you in a little bit what tensors mean. It's not obvious to you probably, but this is an open source library heavily used for deep learning models, which basically is both based on a flow approach and flow graph approach, creating the neural networks. Then once you basically define them in a more graph-like structure. And the beauty for us is it also natively supports CPUs and GPUs that you see a little bit here in different workers. We combine this with Horowat in later lectures to really scale out in clouds. So really use not only one GPU, but very many of them. We will hear there some PhD students from me talking about this. So Keras in the past was a standalone software, but nowadays is also part of the TensorFlow distribution. Still, it's a very nice teaching framework, so to speak. It has a very high level implementation of deep learning in a sense that you do it layer by layer wise, for instance, on top of TensorFlow. And with this, you have a very nice way of quickly understand what you really program. So it's also something what we will learn in lecture 6 and 7, and which makes use, of course, of heavily Python in our case. That's why I just give it here as another good example, which is incredibly often used in Python, basically in cloud computing. I have to admit, PyTorch is also getting momentum, especially because of DDG in it. The distribution engine is also very good for scaling out to many GPUs. We will also touch base on that in later lectures. And deep learning, I already have basically told you all the basics of that in some of the in the prologue lecture. As said, think about the deep learning when we talk about it, not as just adding more neurons here, but basically, not deeper and deeper and deeper just by adding neurons. Here we think about smart layers we add. You see feature maps here, basically and subsampling layers, convolution layers, again, subsampling. So the way you architecture this is basically the idea of deep learning these days. And that's why they have unbelievable breakthroughs in image recognitions, is the modus operandi, and has surpassed any computer vision algorithms that exist in the past. So basically deep learning is there as a cutting edge technology, mostly because it can learn features as opposed to the ideas that we did in traditional machine learning. First, basically had this, and now we have this statement here that more or less features are here and there automatically learned. Obviously, there are always some, like the handwritten characters you see here, that nobody can learn. But this is just the case also for traditional classifiers. And here we see the multi-layer perceptron, the neural networks down in the video here, very nicely by just being a typical neural network that you see here, two-layer network, which is okay, but basically no new innovation. But if you look now on the switch, when they do here in the video, the switch to the convolutional neural network, where we see the right-hand side here, you see all the different feature maps and the ideas of deriving features from the input, how differently you can write a 6, how differently you can write a 9 based on the whole data set. Just for you as a tensor, this is not a really, fancy word really. It's just a way of saying basically interesting things you already know. A vector of dimension 5, you would say, is a one-dimensional tensor, for instance. And then you have two-dimensional tensors, which is nothing else you already know as metrics, right? And there's a three-dimensional tensor that you also sometimes shift here through the neural networks, which is a three-dimensional tensor. So it's basically a general wording for these things you basically already know. And basically that's where the name TensorFlow, for instance, is derived, because when you train and learn such a convolutional neural networks that we have just seen in the video, then you shift along lots of these different tensors and multiply them, always with some functions and so on that we will see also in later lectures. So basically the flow through this neural network is the idea why basically tensors are used. Now for an interesting tool for data analysis on the local side, and this brings us now to the idea, a little bit of understanding what means it to have it on the local computer, is Anaconda. I'm sure if I would be in the classroom and ask who has used it, many of you will already raise their hand. And one idea would be in the last course hour today that you play around a little bit with Anaconda. It's very simple to install on your computer, usually. And it has 6 million users and more. And it's very popular, having all the data science libraries already in it, and especially also the Jupyter environment. So basically you would have on your own laptop, and I demonstrate this here a little bit, essentially a chance to start this. And in your browser, there will be essentially then the Jupyter environment. Important for us in the course is to understand now that this is local. And you see that here always on this local host 8888, right? So this is now very important to realize. And in this Jupyter environment, you can now go to our examples that we have prepared. And it's always local host, right? So you're not in the cloud, you're just on the local machine. And this is now important to understand when you think about cloud computing, like a typical website. For others, that's probably very obvious. And for a website, it is as well. But also when you compute and see something like Jupyter, make sure you always look what's here up in the URI, because there you can easily recognize, are you remote or not? So, and as I said, the Anaconda tool would be something maybe for this course, and actually also for other courses. It is actually quite helpful, I guess, for instance, a machine learning course or so. This is something where I would recommend to download and play around with it, especially in the third course hours today, where we don't have a lecture, it's just a Q&A session, and maybe for you a little bit time to play around with Python and so on. So it is a very interactive tool, the Jupyter tool. For those that don't know it, you have seen it already as a demo now. Basically, this is something where, it's really a very nice tool for data scientists to really quickly play around. You see here some basic example, and I can just go into the cell and say Shift Enter. This is of course very nice, and you would basically in other let's say areas of the course and would switch to different kernels and so on. but the kernel is running in the back, interpreting what's happening here. And you can also restart and clear the output with the kernel, for instance, just if you want to make it more cleaner. And this is also sometimes recommended if you go and start here and do all the different, let's say with Shift Enter, all the different elements. You can also come up again and then have suddenly some interesting mess, or do the last one so that the numbers are not really fitting. And there could be some errors coming in and sneaking in if you're sometimes not getting step by step through a Jupyter notebook, right? So that would be one of the lessons learned. If you have errors in these executions, really go back to the restart kernel and then basically go up here and do it step by step. I will do a demonstration in a bit where you basically can see that. But before I do this, I want to contrast this, of course, a little bit also. And here, what I said already in the practical is already here also on the slides with localhost. The idea of really looking at this, that this is now local on your laptop. But we also want to understand what's the difference now in the cloud. And here we have the Helmholtz Data Federation Cloud that I show you, kind of European Open Science Cloud derivative here for our course. And here we go remote, and you see that in the Jupyter JSC, when I now go remote to this basically Uli Supercomputing Center, you see the website, and the URI that you see here is not anymore localhost. So I'm really remote. I have already opened it to save some time. And now I'm really in a remote environment. You see that here, although it looks, and I will try to increase its font size a bit here, it looks still like we will be on our laptop, right? There's no big difference between this and this. But of course, here the URI says we are now remotely executing something in the cloud. And this is something which is very important to realize. Hence, this will be also demonstrated much more in the second part now, when we do, let's say, more elements about the Python execution itself. But here we have a situation where we are not anymore having one Jupyter notebook. We have the so-called Jupyter Lab infrastructure where you can basically share data, can share elements with other users in the Jupyter Hub and Jupyter Lab with research groups and so forth. You see that a little bit here, that it has also something to do with identity management. Hence, not everybody can, of course, access now the Jupyter JSC. It will be part of your assignment to basically create an account there, to execute elements there, and then the service behind will actually make sure that you're actually allowed to use it. And this is one takeaway message from the clouds, of course. Google Colab is a very specific thing. If you go to other clouds, usually you have to log in, you have to really show your identity, you have to see if you have subscriptions to that particular cloud. And here's the same thing, showing you indirectly with these numbers, while it's not so important to understand really what's happening in all these different numbers, but you see that identity management in clouds can be a very tricky thing. So in this sense, there's lots of things happening behind the, let's say, behind the eye, while the local host has all of that not really to be done, right? So the local host is just on your local computer, on your local laptop. There's no big need for identity management. It's obviously you, the one that operates the laptop. But basically, if you go to the cloud, the situation changed completely. The cloud infrastructure, like the Jupyter Hub we see here remotely, is of course there for many different users in JSC. So hence, you have to really see and map the accounts that you have to the different credentials you provided. Hence, you need a certain login in order to do this, and can, log out, log in based on different credentials here. Can create different Jupyter Labs if you want on different machines. This will be also part of your assignment. Basically, we have a new Jupyter Lab now environment in this course. You will see the ones from last year looks differently. Here are different systems where you can execute this. For instance, here's the HDF cloud I used just for your example here. And of course, it will be one part of the assignment coming up to really get a look and feel on your own, to warm up in the course concerning basically using remotely also Jupyter. And yeah, so this is something which I wanted to bring across in the first part of the course. So really think about that the cloud and web-based interactive developments that you have with this Jupyter is not at all that simple, that localhost with Anaconda or just playing around with scikit-learn in some local installed Python. So here we talk about identity management and lots of elements, but I also can say that it's quite scalable. You see here, we did trainings on that many times with my fellow colleague here, Gabriel, with let's say 30, 40 people, 3 days in a row, just deep learning, just machine learning on these big machines. And it's actually quite stable these days. So we can recommend it as a nice technology to really be used. And I think that's all for me for leave on the table for you for the first part of the course today. And we break here for 10 minutes and then come back for the second part, which has much more demonstrations.